All right, in this video we'll be going over the chapter on sound waves. So there's several small sections. So first introducing sound waves, talking about power and intensity and the decibel scale. Then talking about standing waves. So actually this was a topic relevant even for waves on strings, but this is the more complicated version because the boundary conditions are different depending on the shape of the musical instrument. So we'll focus on those here. A topic relevant to interference called beats, and then a Doppler effect formula. So lots of interesting topics here. Okay, so first of all, in these first sections, we're just introducing sound waves. So sound waves are the main example of a longitudinal kind of wave. So a longitudinal wave, so let me see if I can. So maybe you have gas molecules like this, and then they start to bunch up like this. And then they spread out again. So in this case, you can describe the wave. So you can describe the wave a few different ways. We have three of them right here. So either pressure variations relative to equilibrium, density variations, or the actual displacement of the molecules. So maybe you're probably most familiar with describing things this way. So if you focus on any one particle, it's moving back and forth relative to its equilibrium position. So say this is moving back and forth in the x direction, the wave is also propagating in the x direction. So because the disturbance, which described this way as the displacement, particle displacement, because the particle displacement is in the same direction, parallel or anti-parallel with the direction of wave travel, this is a longitudinal wave. Okay, so we can either describe it using actual distances here or pressures. So we're going to talk more about pressure when we talk about fluids, but pressure is force per unit area. It's proportional to the density of these molecules. So you can see the molecules are more dense here, and they're less dense here. So higher pressure here, lower pressure here. So these molecules are just bunching up, and they're kind of they're propagating each other, the wave forward there. But if you track the motion of any one particle, it doesn't move anywhere overall. It's just going back and forth, as seen with these displacements. Okay, so you'll see sound waves written in any of these sort of forms, but it still has the form of a wave. And I forgot the factor of cosine here for this one, but it's either cosine or a sine of kx minus omega t. For a wave moving in the plus x direction. So I guess it could be minus or plus, the plus sign if it's moving in the minus x direction. Okay. The speed of sound waves is, there's actually a formula similar to the waves on strings formula. So if you remember that the formula for waves on strings look like this, square root of tension over linear mass density of a string. This is for waves on a string. For sound waves, we actually replace tension with something called the bulk modulus, which is kind of like a 3D tension. So tension in a string is how tight it is. So the bulk modulus is it's related to, so there's a definition for it that looks like this. So minus the change in pressure over fractional change in volume. So if you have a material where you decrease the volume by 1%, for example, the denominator there would be 0.01, how much would the pressure go up? So you're trying to compress so it's a measure of like compressibility of something. And it's in units of the same units that pressure has. And the bigger this value is, like the harder it is to compress a material. So for example, the bulk modulus of water is much, much bigger than the bulk modulus of air, because it's a lot easier to compress air than it is to compress water. So this is the analogous item for tension. And then instead of linear mass density, we have just mass density, rho. So this is mass per unit volume. Now when you plug in parameters here, this is V for sound, When you plug in parameters, you actually get a temperature dependence that looks like this. So if you're at atmospheric pressure, and we kind of have room temperature that's roughly 20 degrees Celsius, which is 293 Kelvin. So around room temperature, this is the speed of sound. And if you're not told in the problem what the speed of sound is, you'll take this value. But if you're told a different temperature in the problem, you would use this formula to find the speed of sound as a function of that temperature. And then, as always, we have the speed of sound waves is frequency times wavelength for these sinusoidal waves. So this is still true, but this doesn't determine the wave speed, right? This is a value that depends on the medium. So in other words, if you increase the frequency of sound waves, you decrease the wavelength. You're not going to increase the wave speed. Okay, intensity of waves. So as before, as we've seen with traveling waves, waves on strings, we have intensity is power per unit area. But in 3D, this is maybe more, I don't want to say useful, but it's maybe easier to visualize, like a point source, and then it's radiating equally in all three dimensions. Whereas for waves on strings, you can't really think of it this way. This is called an isotropic source. So there's some energy per unit time that's released by this point source. And how intense these waves are depends on how close you are, right? If there's a total amount of power, say like 1 watt speaker. So you have 1 watt, that's 1 joule per second. Every second it's giving off 1 joule of energy in the form of sound waves. And how intense that sound is depends on how close you are to this thing. So if that power is spread out over this area, so I'm imagining a sphere surrounding it right there, it's going to be a lot more intense than if you surround it with a sphere that's this big, right? That power is spread out over more area. So this is the area over which that power is spread out. So for an isotropic emitter, so it's emitting its power equally in all directions, this area would be 4 pi r squared. So A for isotropic is 4 pi r squared for an isotropic source. Oh, I have it right there. Okay, and then also you can compare. So because the area is proportional to r squared, I is inversely proportional to r squared. So if you have some source, its power is constant, and the intensity is just a function of distance. This value r. R is like the radius. You know, if this is the origin, it's the radius. It's where you are relative to the origin. And so intensity is inversely proportional to r squared. So that's what this formula is saying right there. And then this is another reflection of a statement we made before, where intensity of waves, or power of waves, is proportional to amplitude squared. So we can change the intensity a few different ways. We can make the source more intense, or sorry, I shouldn't say more intense. We can make the source more powerful. So maybe crank up the volume knob on our speaker. Or maybe to get more intense, we can get closer to the speaker, right? Reduce this area over which that power is spread out. So we know a few different ways that we can increase the intensity. This formula tells us how the amplitude of the sound waves is actually changing. So if we make the intensity 4 times bigger, and that means the power, not power, the pressure amplitude, the amplitude of waves is going to be twice as big, right? Because of this square right here. So 2 squared equals 4. Right? It's again this property that power is proportional to amplitude squared. And by the way, you might wonder, well, you know, amplitude, we could also have density, and we have a density right here. The one on the bottom is absolute density, and the wave description right here, this is density variations, which are very small compared to the overall density. So this denominator wouldn't change, even though the numerator would change, even if it was written in terms of density, because the density variation is small compared to the overall density. Another topic related to intensity of sound waves. So SI units would be watts per square meter. So watts for power and square meters for area. Decibels is another non-SI unit. it's a logarithmic scale. So for every factor of 10 in absolute intensity that you grow, you only gain 10 decibels. Okay, so the zero reference point, so what we call 0 decibels is just kind of like an agreed upon value, just a constant that is kind of relevant for humans. This is kind of the smallest intensity of sound waves that humans can hear. Okay, so any sound less intense than this, it's probably not audible. So 0 decibels is defined to be this reference intensity. So this value, 10 to the minus 12 watts per square meter, is I naught, reference intensity. And that's written down right here. So that's where our scale starts, at 0 decibels. And then for every factor of 10, we get 10 higher on the left-hand side. So in other words, multiply by 10 on the right-hand side. For every time you multiply by 10 here, you add 10 decibels here. So 0, 10, 20, 30, that means 10 to the minus 12, 10 to the minus 11, 10 to the minus 10, etc., watts per square meter. So by the time you get to 1 watt per square meter on the right-hand side, that's going to be 120 decibels on the left-hand side. And that's extremely loud. That's like, what textbooks always have is like, you're at a rock concert. They love complaining about how loud a rock concert is. But that's about 120 decibels. 130, 140, that's like you're getting close to a jet engine, and you'll start to have, well, already at 120 decibels, if you're there long enough, you'll have permanent ear damage. And then 130, 140 decibels, you don't have to, you'll have damage pretty quickly there. Okay, so this is the formula that will relate one to the other. So if you, if you have 60 decibels, it's easy to guess the right-hand side here. But if you have like 64 decibels, you want an exact formula to guess the right-hand side here. And that's given via this formula right here. So you plug in 10 to the minus 12 here. And then if you knew like this was 64 decibels, you plug that in there, and then you could solve for the absolute intensity in watts per square meter. Yeah. Okay, standing waves. Okay, so if you have a musical instrument, so let's first focus on the left-hand side here. You have a pipe that's closed on one end and open on the other end, and you say hit it with a hammer. So it's going to excite a bunch of sound waves inside it of all sorts of different frequencies. But the ones that persist over time are the ones where when the waves bounce back and forth between the two ends, they don't destructively interfere. So there are special frequencies where when they bounce back and forth, they kind of reinforce each other, that the waves add up and they don't totally cancel each other out on average. And visually, it's nice to see these frequencies actually correspond to very nice shapes right here. So I'll put these back in, but I'm going to delete these for now. So this blue graph right here is the fundamental frequency. And what I drew here is a node on the left-hand side. For the closed end, this is a displacement node. So in other words, if any particles right here, they don't have enough room, so I'm not drawing it right here because I'm for space. But a particle on the edge doesn't have room to move back left and right. So the displacement of the sound wave right there has to be 0. There's just not room for it to keep going back and forth next to the edge. So that's a displacement node. And here it's totally free to move left and right. This is a displacement antinode. So the wave with the longest frequency that can fit, that can satisfy those two boundary conditions, that's the fundamental frequency. And actually that's where most of the energy remains in the sound wave after you strike it. So you strike it, you let some of the destructive waves cancel out, and most of the energy is in this fundamental frequency. And then, so any wave that you could fit in here that satisfies those boundary conditions will also work. So if I look at this, like the red one is the next one that fits in there. This is the first overtone. So you'll notice that there's a displacement node right there, and a displacement antinode right here. But then there's also another node right there. So what these look like is, so this is at one moment in time. What the wave is going to look like a quarter cycle later is look like this. It's just going to be flat. And then another quarter cycle, it looks like this. So what this is saying is that this is like, so if you have a particle here, it's moving back and forth with a big amplitude. Here, this is moving back and forth with an amplitude that's smaller. Here, it's moving back and forth with an amplitude that's even smaller than that. And then right here, this one isn't moving back and forth. So this graph is just saying how big the amplitude is as a function of position. So if these were the equilibrium spots of all of these particles, at this moment in time, this is the farthest away. This one's less far away. This one's even less far away. So that's where the particles are at one moment in time. At a quarter of a period later, they're all at their equilibrium positions. And then another quarter of a period later, they're on the other side. So this graph contains a lot of information all at the same time. This is saying the displacement, the overall amplitude as a function of position. Yeah, and there's a bunch of different frequencies for this. Okay, so this red one's called the first overtone. This is the second overtone. So if we were to draw, instead of displacement nodes and antinodes, I'm going to explain the statement right here. If we were to describe pressure nodes and antinodes, then the nodes and the antinodes would flip. So in other words, if you were to draw pressure nodes and antinodes, this would be a maximum and this would be the node. And this has to do with, well, this is open to the atmosphere, so its pressure variation is going to be 0. It's going to have the same pressure as atmosphere. Whereas you can have high or low pressures right here, just because it's closed. So you can, the biggest variation of pressure would occur at the endpoint right there. Yeah. So what's easiest to do here is to draw the standing wave, and then you can kind of just visually see what the relationship is between the length of the pipe. So the length of the pipe is just from one end to the other right here. And then the wavelength is how long is it to complete the wave. So you'll see for the blue one, like this is only a quarter of a wave. We would have to extend it here, here, here. So we'd need 4 times the length of the pipe for one whole wavelength for the blue one. And that's where this formula comes from. For the red one, we're almost the way there. We're 3/4 of the way there, but then we need 1 more fourth. So we need 4/3 times the length of the pipe to finish that wave. So you can start to see the pattern here as you go to higher and higher overtones. It's 4L over 1 for this one. 4L over 1, 4L over 3, 4L over 5. You can probably guess the next one is going to be 4L over 7. And that will be the next wavelength for the next overtone. So this is slightly different in the open case. This is just a different boundary condition. So the displacement antinodes, there's an antinode at both ends. Now, if we just drew antinode straight over to antinode, that's not a wave, or it would have infinite wavelength and 0 frequency. So we're not really interested in that because we're not going to wait an infinite amount of time. So the fundamental here is one antinode to the other, and that's this. And then again, you can see the pattern here. 2L over 1, 2L over 2, 2L over 3, etc. So the next one would be 2L over 4 for the next wavelength. Beats. So this is an artifact. So standing waves is an artifact of interference, just waves bouncing at the boundary and then interfering, and this is these are the waves that sort of survive. Beats is another phenomenon related to interference of sound waves. And this has to do with sound waves that are almost the same frequency, but not exactly the same. So if you have like 2 tuning forks and one is at 440 hertz and one is at 441 hertz, maybe a better example is suppose you're tuning a musical instrument, right? You have a violin, you're next to a piano, and you play the piano key, which is, let's say it's in tune, and then your violin is slightly out of tune, and you play them both at the same time. You'll hear kind of a wobbly, like wow, 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 wow. So what you're hearing is actually the beat frequency. So what happens when you superimpose these two notes on top of each other, you get a graph that looks like this. And this shrinks down to 0 right here as long as the amplitude of the two waves is the same. So what happens when you add together these two waves, so you can go through the math, you just use this fact and go through the math to see that you actually get an amplitude that goes close to 0 over time, and then with its own frequency. And then on top of that, you have the wave wiggling around inside that envelope. So the frequency of the overall wave, the small wiggles right there, is governed by the average of those two frequencies. And then this overall envelope, this wow, 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 that's the beat frequency. And that's the difference between the two frequencies. So if you have your violin playing and the piano playing and it's 440 hertz and 441 hertz, then every 1 second you're going to hear it loud. So this, and then it'll be loud again 1 second later. So if you hear a wow, 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 that would be like 4 hertz for the beat frequency. That means the violin is even farther off from being in tune from the piano. So you try and get that wobble down with as big a period or as small a beat frequency as possible. Okay. The last topic that we would like you to look at in depth has to do with the Doppler effect. So this is a source of sound waves, and you have some observer of sound waves. So I don't know how to draw a phone. Looks like a Pac-Man monster. This is supposed to be a phone. Maybe an iPhone would be better. So you have a source of sound waves and then an observer. And maybe the source is moving towards the observer and the observer is stationary. Or maybe they're both moving towards each other. Maybe the source is at rest and the observer is moving towards, etc. So the observer has some V observed, and the source has some V source. So the magnitude of these two speeds goes here, and here for V observed and V source. The V here is the speed of sound. So this is 343 meters per second, remember, for the speed of sound at room temperature. Or if you're told the temperature, you could refine that number a little bit. So maybe I should. So this is the source frequency. So the source is giving off sound waves of some frequency. And this is the observed frequency. So sometimes you'll write out the words source and observed. Sometimes you'll just have F naught. That means original frequency, and then F prime for the modified frequency. So the frequency of sound waves heard is not necessarily the same as that given off by the source. And so you would use this formula to figure it out. And the hardest part of using this formula is deciding whether you're going to choose the plus or the minus sign in the numerator and the denominator. And the decision of whether you choose the plus or the minus, I guess I could quickly sum it up. So you kind of just choose, so you know that whenever one object is moving towards the other one, F prime is bigger than F. So whenever like the observer is going towards the source or the source is going towards the observer, that tends to make this bigger than this. So that would be a plus on the numerator or a minus on the denominator, right? Those two choices of sign would increase the fraction. So if this was the case, if the source was moving towards the observer and the observer was moving towards the source, we would choose a plus and a minus, like that. And then put in the magnitude of the speed right there for how fast the observer is moving, how fast the source is moving. If the observer wasn't moving at all and the source was moving away, then you'd plug in 0 right here, and it wouldn't matter whether it's a plus or minus because it's 0. And then for this one, you would do, so the source is moving away, so it's the observer is going to hear sound waves of lower frequency, and that would be a plus on the denominator. So for a source moving away from the observer, you choose plus on the denominator, and then the top is just going to be 0 right here. Yeah, so there's more to study associated with this. I mean, it's so you might want to go through where this formula comes from. So it's actually tracking like why the frequency is different. So when the observer is moving, it's actually because they're encountering wave crests at a different rate because they're moving faster through the medium. Whereas if the source is moving, the wave crests kind of either bunch up or spread out. So there's some nice pictures in the book that explain where this formula comes from. Yeah, that overall gives a summary of all these topics. So definitely more information than what's covered here, but this is the overall summary. Good luck with all the sound waves topics.